This is the 2016 free response questions 1 through 6. However, we are not going to, in this video, look at question number 5. This is mainly designed for the year 2020, and we will not be having any area volume questions on our test this year, so I will go skip over that one. So in problem number 1, let me read the prompt. Water is pumped into a tank at a rate of modeled by W of T, that's measured in liters per hour for 0 to 8 hours, where T is measured in hours. Water is removed from the tank at a rate modeled by R of T liters per hour, where R is differentiable and decreasing on the closed interval from 0 to 8. Selected values of R of T are shown in the table above. At time t equals 0, there are 50,000 liters of water. So mainly in this video, I'm going to highlight the annotations that I've already provided for you that support your learning in this. For those of you who are in my class, you can access these answers. So the first thing I want you to notice and pay attention to is that we are looking at a classic in-rate, out-rate problem. They told us that we have water that is pumped into a tank at a rate of W of T, and water being pumped out of a tank or removed from a tank at a rate R of T. So one of the key things is to remember that both W and R are rates, and they're both measured in liters per hour. Something important to remember in an in-rate, out-rate problem is that somewhere in the problem you're going to need to put together the fact that the total rate of water that's in the tank is going to be affected by the in rate minus the out rate. The other thing to pay attention to is that they tell us that R of T is differentiable, which implies that the function for the amount of water being pumped into the tank is continuous, and that there is an initial condition of 50,000 liters of water in the tank at time 0. Question or letter A. In letter A, they are asking us to estimate let me just clean this up a little bit. They're asking us to estimate R prime of 2 and show the work that leads to your answer, and you need to indicate units of measure. So when we're estimating an instant rate using a table of values, we know that we're going to go, 2 would lie between 1 and 3, so it would be in here. So we're going to go 1 data value above and 1 data value below, and we're just simply going to do the average rate of change to determine or approximate the instant rate. So what we're looking for in letter A, as you can see, is I'm looking for that difference quotient that I have to see. You do not have to have the R of 3 minus R of 1, and you do not necessarily have to get to a number of negative 120. However, in this problem, units are required, so since R was measured in liters per hour, the derivative of R would be measured in liters per hour squared. In letter B, they are asking us about the total amount of water in the tank. So in letter B, they want us to use a left Riemann sum. They want us to use 4 subintervals as indicated by the table to estimate the total amount of water in the tank during the 8 hours. And then they want us to decide whether we're going to have an overestimate or an underestimate. Now remember, in the prompt, they told us that R is a decreasing function. That's going to be really important to answer this question. And the way we're going to figure out whether we have an overestimate or an underestimate is we're just going to draw a decreasing function, and we're going to put in rectangles, and we're going to make that decision. When we accumulate using a left Riemann sum, let's go back and think about that again. So let's go back up to the table, and let's get rid of the information that we already have here. So when we do a left Riemann sum, they told us to put in 4 subintervals. So we're going to have 1, 2, 3, 4 subintervals. And since it's a left Riemann sum, the width of the first rectangle from 0 to 1 is going to be 1, and the first left endpoint is 1340. From 1 to 3 is 2. The second left endpoint is going to be 1190. from 3 to 6 is 3, multiplied by the next left endpoint, which is 950. And from 6 to 8 is 2, multiplied by the last left endpoint, which is 740. So when you see the work down here, also remember, since we're getting the total amount of water, we're going to accumulate. So I'd like to see and I'd like for you to tell me that you're accumulating from 0 to 8 of R of t. This row I don't really care about. You can write it if you want to, but this is the row that I really care about, and I really need to see on your paper. And as I've tried to remind you over and over and over again, you do not have to get to 80/50, but you can. The second part of the question, remember I talked about the fact that we're going to have a decreasing function. So I drew a decreasing function on my paper, and I put in a few left rectangles, and I can clearly see that I am beginning to overestimate the area. So I'm going to say this value is an overestimate since R is a decreasing function. And this is just for me to see that I'm going to get that overestimate. All right, and then in letter C, they want us to determine, they're telling us to use our answer from part B to find an estimate of the total amount, there it is, that word total amount of water in the tank to the nearest liter, so they want me to round off, at the end of 8 hours. Now remember, the total amount of water requires the accumulation of the total rate. So I'm going to accumulate area, the in rate minus the out rate, and I'm going to add any initial condition that I have, which in this case, remember, was 50,000 liters of water. So I'm going to begin with the setup of my work. There's the initial condition of the 50,000. This is me accumulating the water that's going into the tank, and then this is me subtracting out the amount of water that I accumulated in part B, which is going out of the tank. And what you see in the box right here is sufficient. I do not have to combine that to get to the 49,786 or 49,786 liters. And then finally, part D. If there's going to be a tricky part in this question, it's a little bit tricky in part D. It's not the hardest question. In part D, for 0 to 8, is there a time? So is there a time almost always launches you into a theorem. It's a theorem trigger. You have to just decide which theorem that we're going to be dealing with here, and this can be a bit tricky, and you must include the conditions of the theorem. All right, so let's go back up and finish what they told us to do. Is there a time when the rate of water pumped into the tank, so the in rate, is the same, that's equal to, as the rate at which water is removed from the tank, which is the out rate? So basically they're saying, does the in rate ever equal the out rate? Well, let's come down here and take a look at my work. I think I have a pretty clear explanation in part D. So this actually is the intermediate value theorem. And you may be wondering, how is it the intermediate value theorem? A lot of kids probably think, because we're dealing with rates, that we're dealing with the mean value theorem, but we're not. This is really asking us, in other words, so let's look down here. Don't worry about the College Board work. Look at my work down here, or my explanation. In this problem, we want to know, in this problem that, that's really, I need to fix that. In this problem, we want to know if the two rates equal each other. So we really want to know, look right over here, we want to know if W of t is equal to R of t, which is really the same thing as saying that the in rate minus the out rate is equal to 0. In other words, I can subtract R of t to the left side, and I can end up with the statement right here. So it's really saying, to say that the two rates, the in rate's equal to the out rate, is really to say that the total rate equals to 0. So I'm asking if Wt minus R of t is equal to 0. Does the total rate equal a y value of 0? We're not taking the derivative of Wt and R of t. They just happen to be rates. And we want to know if those rates ever equal to a y value of 0. So that's why we're in the intermediate value theorem. So then, since I know I'm in a theorem, the condition of the intermediate value theorem, recall, is that the rate that we're considering, or the function that we're considering, must be continuous on 0 to 8, which is true because they told us that in the prompt. So then I want to determine the total rate at 0, and I'm going to use my calculator to do that. Using the table and the function that they gave me, I get 660. And then I'm going to determine the total rate at 8 using my calculator, and I get negative 618.476. Since 0 is between these two numbers, then I can say that the total rate will definitely equal 0 by the intermediate value theorem, which means that W of t is equal to R of t. Now, there are other ways to show this, but you might need to ask me to read your answer, or you might need to read it to me to see if you're going to get credit for that. So that's question number 1. And if you're in my class, you have access to looking at my work, my handwritten work, just to show you how I would have written this up. This is really not that difficult of a question. Like I said, part D is probably the most thought-provoking part of the question. All right, let's go on to number 2. In problem number 2, we have a particle moving along the x-axis, which just simply means that the particle is just going back and forth along the x-axis. The velocity of the particle is given at time t is given by v of t. So we have the velocity function given. And remember, this is question number 2. It is a calculator question. The position of the particle at x equal to 2, the position is x equal to 2 at t equal to 4. So when the time is 4, the position is 2. This is my initial position. Letter A. At t equal to 4, is the particle speeding up or slowing down? And you know that speed, you must consider both v of t and a of t. If velocity and acceleration have the same sign, then the particle is speeding up. If velocity and acceleration have opposite signs, then the particle is slowing down. So I'm going to have to determine both the velocity and the acceleration at 4. I'm going to totally use my calculator for that. I'm not doing anything by hand. So I would have the function into y1, and then I would make the calculator find the derivative at that particular value. And I see that the velocity at that time is positive, and the acceleration at that time is negative. So I'm going to say that the particle is slowing down since velocity and acceleration have different signs. And you do need to make that conclusion. All right, going back to letter B. In letter B, we're looking for all times when the particle changes direction. Remember from position, velocity, acceleration that a particle changes directions when the velocity changes sign. So I'm going to use my calculator. I'm going to graph. I'm going to have y1 equal to v of t. I'm going to take a look at that graph. I'm going to easily be able to see, using my calculator, that the velocity function changes sign at 2.707. I get 1 point for finding the value where the velocity changes signs, and then I'm going to clearly state what I see. V of t changes, and I don't really have to say positive to negative. That gives a little bit stronger argument, but I can say changes sign at t equal to 2.707. Therefore, the particle does change directions. All right, moving on to letter C. Find the position at t of the particle at t equal to 0. It's important to remember that when you're finding position, position needs the initial position plus the accumulation of area under v of t. So let's take a look at our answer. So we had an initial condition that the particle is at 2. No, I have that backwards. At 4 seconds, the particle is at 2. So this is going to be where I start, and so that initial condition was really important to this problem. That's going to be where I start the accumulation of area. So over here, when I look at the definite integral that I'm going to write, there's 1 point for the integral, so it doesn't necessarily have to include the initial condition at this point. So even if you never included the initial condition, if you had the definite integral, you also could have that definite integral with the bounds reversed with a negative in front of it. You get 1 point. You get 1 point for adding in the initial condition somewhere, and then you get 1 point for your final answer. And then in letter D, they're going to move on from position, and now they're going to pick up the total distance traveled. And when you're finding total distance traveled, you do not need the initial position, but you should take the put the absolute value around v of t, not the integral, in order to accumulate the total distance traveled. So in my calculator, I'm going to accumulate or integrate from 0 to 3. I'm going to put absolute value around the velocity function and get a value of 5.301. No initial condition in this problem. Moving on to, and this is my work on question number 2, just so you can see how I wrote it up. Again, you'll notice it didn't do a whole lot of writing. I didn't take up a whole lot of space. Pretty straightforward. Number 3 is our classic geometry problem, and we're going to need to calculate, it looks like, the area of several triangles. Let's read the prompt. Pretty short prompt. The figure above shows the graph of the piecewise linear function. Again, remember, piecewise linear simply means we have a function that's made up of pieces of lines. So we have several line segments coming together to form our graph. And the name of the graph is f. And up here, they're telling us that for sure this is the graph of f. Now we have another function whose name is g, and g is defined to be a definite integral. So if I want to find a g value, I accumulate area starting at 2 to wherever I need to go. But more importantly, since g is a definite integral, then by the fundamental theorem of calculus part 2, g prime of x is equal to f of x. And notice I included it way back up here, and you're going to see me write that many times so that I make sure that I get my connection point. All right, looking at letter A. Does G have a relative minimum, a relative maximum, or neither at x equal to 10? So I'm going to look back up at the graph. Remember, this is the graph of G prime up here. F is equal to G prime. So when I go to x equal to 10, what I notice is that G prime of 10 is equal to 0, but G prime does not change signs. So 10 is only a critical number, but it becomes neither a relative max nor a relative minimum. So in letter A, notice the first thing that they're looking for is that connection point. The student declared, they told us that G prime of x is equal to f of x. In any part, if we find it anywhere, then the student gets credit for that. Secondly, we're looking for the student to tell us that there is neither a relative minimum nor a relative maximum at x equal to 10, because G prime of x, or, it doesn't have to say both, or f of x does not change. So you could simply say does not change signs at x equal to 10. All right, let's go back to letter B. In letter B, does the graph of G have a point of inflection at x equal to 4? So remember, since we have the graph of G prime above, which is f, wherever G prime has a local max or a local min, or changes from increase to decrease or decrease to increase, the G original has a point of inflection, and you can get this directly. Both of these parts were from the All About Me sheet. So when I go back up and look at x equal to 4 on the given graph, I see a local maximum. Now we've seen this before. Do not decide that nothing is happening there because you see a sharp turn and you think that there's no derivative there. There is a G prime value. G prime does have a local maximum at x equal to 4. Therefore, G original has a point of inflection at that value. So we're looking in part B for the student to say, G has a point of inflection at x equal to 4 because G prime of x or f of x changes from increase to decrease, or could say has a local maximum at x equal to 4. 1 point for the answer with the correct justification. Going back to part C. In part C, now we're looking for the absolute minimum, and the absolute minimum launches us into the extreme value theorem. We're going to need to find the critical numbers by setting G prime, which is f of, not setting necessarily, we're going to look at the graph, and we have to consider the endpoints. Once we figure those values out, we're going to accumulate that area from 2. Remember, 2 is our starting place as defined by the integral of G. Let's look back up here at that. So whenever we're finding a G value, we accumulate areas starting at 2. So that's going to be really important. And then we're going to make a table of values, and we're going to compare those Y values. So in letter C, we determined that G prime of x, which is f of x, changes signs at -2 and 6. So those are our critical numbers, and we get 1 point for considering those. Now you could list other critical numbers. I think 10 was a critical number. 10 is a critical number. 2 is a critical number. 10 is a critical number. And if you declared them as critical numbers, it's perfectly fine. There's nothing wrong with that. But the ones that we have to see are -2 and 6 because they're potential candidates. And then we have our endpoints of -4 and 12. To get these values right here, the -4, the -8, the 8, the -4, each one of those was found by accumulating the area starting at 2, going to, for example, for the first value, -4 under f of x or G prime of x dx. And on the next page, I'm going to turn there for just a second, you will see that I had accumulated or determined the areas of all these various triangles. Now, when I wrote the signs, as you can see right here, when I included this as negative and positive, I was just looking at whether the area is below the x-axis or above the x-axis. But remember, if I'm starting with 2 and I'm going back in the opposite direction, then both of these 4s would both be negative, and this 4 would be positive. So just be careful of that. And so I used those areas from the finding the area of all those triangles to accumulate using an integral each value to get these values. This is my justification. A lot of times students will say, well, what's the justification? It's that table right there. You doing the work of giving the Y values and comparing them. And that's all I have to say about that. And then looking at letter D. In letter D, this is really all about area. From -4 to 12, find all intervals for which G of x is less than or equal to 0. So you've got to carefully consider where the net accumulated area, because they're looking for the G original. And remember, G original always starts at 2, goes to the Y value in question under f of x dx. So I'm going to start at 2, and I'm going to go to -4, and then 2 to 12, and then I'm going to determine where the areas are positive and negative. And I'm going to use these areas that I found again before to figure that out. And so G of x is negative from -4 to 2 and from 10 to 12, because the overall value of those regions would give you a net area of negative. Problem number 4 is a differential equation and a slope field problem. When you're doing a slope field, it's really easy, but it's also really easy to make a silly arithmetic error and lose points. So letter A, we're just simply sketching a slope field by substituting the xy values at the given points that they've indicated. Now notice they did not put any points in here. We're only looking 1, 2, 3, 4, 5, 6 values to create the slopes. So when you look at those 6 values, you have to make sure that all of the non-zero slopes are positive or negative. So I need to see an increasing, I need to see an increase, I need to see a decrease, and a decrease, or positive slope, negative slope, and then for the zeros, we're going to get those points. So if you missed any one of these, positive or negative, you had it going in the wrong direction, you're going to lose that 1 point. And that's why I'm saying be careful when you do your arithmetic. In part B, f of x is the particular solution. Now, they're not telling us to find it right now. They're just saying f of x is the particular solution with an initial condition of 2, 3. So we have that initial condition of 2, 3. Write the equation of the line tangent to the graph of f of x at x equal to 2. Very, very easy problem. Can't lose any points here. So we start with y minus y1 is equal to m times x minus x1. We're going to substitute 2 and 3, or 2, 3, into the slope generator, which is the differential equation, and we're going to get a slope of 9. We're going to substitute the point 2 and 3 in place of x and y. So the equation of my line with y by itself looks like this. You don't have to distribute and combine like terms. And then secondly, they wanted me to approximate the y value at 2.1. So notice that this answer right here in the box is totally fine. I do not have to subtract and multiply and add 3. I do not have to get 3.9. I can leave my answer as how I see it right here for full credit. And then part C is finally where they're telling us to solve the differential equation, find the particular solution, y equal f of x, and this means that it's time to do the separate, integrate, solve using the initial condition. Now, when you look at my work, you're going to see a couple of things, and I'll show you in just a second. So the first point is for the separation of our variables. So we need a good separation here, and that would be, let me move this out of the way. Give me 1 second there, that's right in the way. So this is my good separation right here. It can have the integrals with it or not with it. You do not have to have these integrals in there. You won't lose any points if you forgot to write the integrals. Then we're going to get 2 points for the antiderivatives, 1 for the left-hand side. Be really careful that this is not a real hard one. And 1 point on the right side. And 1 point for the constant of integration and using the initial condition, meaning that we're going to substitute the x and y value that they gave us. Now this is where you have a decision to make. You have to decide if you're going to substitute the x and y value and solve for c first, or if you're going to solve for y first. So over here in the College Board work, they decided to substitute the x and y value of 2, 3 first. And so here's the 2 being substituted, and here's the 3 being substituted. And then they went on from there to get a c value of negative 1/3, because 2 minus 1 is 0 here, and the ln of 0, 2 minus 1 is 1, and the ln of 1 is equal to 0. So c is negative 1/3, and they substitute it back in here. And then you get y by itself, basically by dividing both sides by 1 and flipping the fraction. It's okay to be a complex fraction. Now the other option is, if you come back to this point right here, instead of solving for c first, you could solve for y. So to solve for y, is the same thing. Flip the fraction on both sides, because if 2 fractions are equal, their reciprocals are also equal. Then we can divide by negative 1, substitute the 3 and the 2, or the 2 for x and the 3 for y, solve for c, and substitute it back in place of c and get the same thing that they had, and you do not have to state the domain. All right, one more to go because we're and these are my answers somewhere down here. Let's pull that up just in case you want to see them. I got the same answers. There's my slow, notice how slowly and carefully, look how many steps I use because that last point solve for y, it's only 1 point, so I want to be real careful not to lose it. All right, we're not going to look at question 5 in this video, but we are going to go on and look at question number 6, which is a symbolic derivative. So they give us a table of values. They give us information about a function whose name is f and a function whose name is g. F and g have continuous second derivatives. Well, that's kind of important because that tells me that f prime wait a minute. Yes, that tells me that f prime is differentiable and the original and the first derivatives are also continuous. So they start in letter A by referencing a brand new function whose name is k of x. K of x is an inside-outside function, has a composition. G is the inside and f is the outside. And they want us to write the equation of a line tangent to k at x equal to 3. So to write the equation of a line, we're going to start with y minus y1. Let me write that down. Y minus y1, that informs my work, is equal to m times x minus x1. So the first thing I'm going to have to do is figure out the y value when x is 3 by using the table. So I would have to do f of g of 3. Be careful when pulling numbers out of the table. That's one of the most common mistakes to make. And then I'm going to need to find the slope, which means I need the derivative of k, which means I need the chain rule because I have an outside and an inside function. So I take the derivative of the outside, leave the inside alone, multiplied by the derivative of the inside, and I have to be really, really careful going through the table to get the values that I need. And I get a slope of 10, so I'm going to substitute that into the equation of my line, and this is the equation with y by itself. All right, moving on to letter B. Again, this one is one that you really can get a lot of points on. It's really not that hard. Just be careful of grabbing the right numbers out of the table. In letter B, h of x is comprised of a quotient. So we're going to need the quotient rule. Down d up minus up d down over down down. And we just want to generate the derivative at 1. So when you come down and look at the work, you can very clearly see the quotient rule, down d up minus up d down over down down. You may not leave your answer like you see in the blue box. That's just the first step. You may leave your answer as to what you see here in the pink box. You can stop right there, which is perfectly fine, or you could take it one more step, which I don't really want you to, because it saves time to leave it, and secondly, you can make a silly mistake. And of course, the answer of -3/2 would also be acceptable. So we have to see the expression, we have to see the quotient rule in action, and then we have to see some form of the final answer. And then the last part of number 6 is letter C. We are evaluating a definite integral. All right, so if we're going to differentiate f double prime, we're going to get back f prime. I think I said differentiate. If we're going to integrate f double prime, if you integrate f double prime dx, you're going to get back to f prime. All right? Also, though, there is an inside function right here. 2x is inside. So when we integrate with an inside function, we are going to need u substitution. And you'll see my u substitution work down below. So down here, I let u equal to the inside function of 2x, take the derivative of both sides. I don't need the coefficient of 2, so I'm going to divide both sides by 2 and get the 1/2. I'm going to substitute, so there's the 1/2 in front, substituting u in place of 2x, which is there. Now, instead of changing the work back into terms of x, I decided to change my bounds, so I'm going to substitute 1 in place of x, and that gives me a low bound of 2. I'm going to substitute 3 in place of x, and that gives me a high bound of 6. And I can see that I left off my 1/2 from this. That's a good thing I'm looking at this right now. So that's just going to be f prime at 6 minus f prime at 2 times 1/2, which is what you can see here. Now that's not enough. That's going to give you the antiderivative points. But I have to see the numbers appear. You may not leave f of, g of, f prime of, or whatever. So we at least have to get this to get to that answer point. And when you look at my work, you'll see that I did the same thing. And there it is. So this is the 2016.